So we were talking about COCOMO and how COCOMO is used by project managers in software engineering management to predict as to how much time and effort it would take to develop a project or software based on certain parameters. Now, these parameters are predefined as it was given by Barry Boehm in 1981. Now, the problem in today's world is that when Barry Boehm gave this model in 1981, it was based on linear regression of the 63 projects that he chose. And as you can see, from 1981 to 2020 or 2016-17, when this paper was published, the type of projects, the type of software that develop, they tend to change, they tend to evolve. So what the problem software managements or the people who used to do the cost and time estimation of software, the estimation didn't prove correct, or there were a lot of gaps and lapses in between. So that is why in this paper they tried to optimize the coefficients of because as you can see, based on the equation of constructive cost model, it is dependent on certain parameters which you can say they are dynamic. For example, lines of code. It depends as to how much you think your software is going to be. But the parameters that you can see in the equation C, A, B, C, and D, they're predefined. Although they're not predefined for all the projects, they're predefined based on the lines of code, because COCOMO divides projects based on semi-detached, organic, or intermediate, and all these three differentiations are done based on the number of lines of code. So as you can see in this, what the authors of the paper tried to do, they tried to optimize A, B, C, and D based on genetic algorithm. So they made the genetic algorithm, because like I told you, the termination condition is your algorithm terminates on two things. One, if you have a predefined value in mind that you want your algorithm to converge to, or if you do not know where your algorithm is going to converge, you keep a termination condition based on different things. In this algorithm, the termination condition was kept that this algorithm needed to run to 1500 generations. So as you can see, what happened in this, so they used, this is, as you can see, the chromosome A, B, C, and D. Now each chromosome has, A, B, C, D is the population, okay, and A, B, C, and D are the initial chromosomes, and all these 4 bits, they are the genes. Now as you can see, in this gene, the first bit was the integer, and the other 3 are the decimal points, after the decimal points. So they started with certain things, certain population. They started with certain random population. They randomly chose the values of A, B, C, and D, and then they assigned some fitness values. Now what is the fitness value? The fitness value was based on this equation. So the time that it took, because we are in this paper, what the authors did, they drew parallels between 3 things. One, the actual cost and time of the project that was gauged at the completion of the project. One, the cost and time that was estimated using the conventional COCOMO model, and the cost and time that was estimated by the GA. Now the fitness function is that the cost, the theta means the development time or the man hours that was gauged at the end of the project, minus the one that is predicted, and divided by the actual one. So as you can see in this one, as like I told you, parallels were drawn between 3 things. One is the actual development time, one is the development time that was predicted by a genetic algorithm, and one was that was done by the conventional COCOMO, in which the parameters were not optimized. As you can see, in project 1, it took 21 man months, which is less than 2 years. Now the optimized COCOMO model as per the GA, it predicted 18 as against the one that was predicted by the conventional COCOMO, which was 12. So as you can see, there's a lot of gap between 21 and 12 as compared to 18 and 21. And the fitness, if you can see, the fitness is also increasing. So all these parameters that was, so as you can see, the original value of coefficient A is 2.04, and the optimized value that came with the help of genetic algorithm was 2.312, and same was for B, C, and D. So this algorithm, it ran for 1500 generations based on the things that you already know. It started with an initial population, and then the fitness function. It performed selection based on fitness function that I already showed to you what that fitness function was, and then it performed crossover, mutation, and all the other things. And in this one, the mutation in the crossover 3-point mutation was chosen, and like I told you, it ran for 1500 generations. So this was one of the applications wherein GA was used in research recently. Now let's talk about the various application areas where you use genetic algorithms. Number one is obviously the optimization, because it is largely and mostly used in optimization problems where you do not know the actual solution, so you just choose the best among all the possible solutions. It's also used in robotics because it can give you the optimum trajectory for the trajectory of the robo, wherein the robo arm moves from one point to another. It's also used in design of semiconductor layouts, or like I showed you in the previous video, you saw how a car evolved from one design to another. So it's used in car design, and mostly it's being used in a lot of disease-related issues. It can predict brain tumors, or it can predict heart attacks and all that stuff.